Hello guys, and welcome to another calculus video. In this video, another episode of the Advanced Integration Guide, we are going to be going over the Laplace transform. Now I want to go and do a quick disclaimer. We're specifically talking about using the Laplace transform for solving integrals, as you can see in the title. So this is not going to teach you how to use the Laplace transform for differential equations, though the idea is pretty similar. So let's go ahead and jump right into it. So before we get started, we're going to discuss, of course, why do we want to use this method? And so there's several reasons, and there's actually very many different ways to use the Laplace transform. So one reason is that many integrals already look like a Laplace transform, which just means sometimes solving the integral directly might be kind of nasty, but using the definition and the rules of the Laplace transform, we're going to be able to solve it more easily because of all the rules that we have in the Laplace transform that are helpful to us. So some other integrals can be converted into the Laplace transforms, which again are pretty easy to calculate using all the rules we have access to, and then we can manipulate them easily, and they work nice with other typical functions. Also, the Laplace transform can be used as an operator on a function which transforms obviously transforms, right? Transform from one class to another. They can also easily be used with complex numbers and alternate definitions of real valued functions, and they have a variety of identities and rules that make integration easier. So let's go ahead and jump right into it. So first of all, on comment on my recent video on one of my recent videos said that I should spend a little bit more time discussing rigor, which I think is an absolutely great idea. On my videos, I almost always interchange the order of integration or summation or something like that without any real justification. So, if this isn't important to you, I'd suggest you just skip this little section. But if it is, then this is definitely going to be very interesting. So, in this video, we're going to be interchanging the order of integration many, many times. And the reason that we're able to do this is something called Fubini's theorem. So essentially, if the integral over some region of x and y with respect to x and y or with respect to area, um, if the integral of the absolute value of the function over this region is less than positive infinity, then we are allowed to write this as the integral on x and then the integral on y, or the integral on y and then the integral on x. So essentially, if we want to interchange the order of integration, what we need to do first is put those absolute value bars on f of x and see if the integral is still going to converge. So if you have a function that is purely positive, then you know that as long as the overall integral converges, of course the absolute value is going to converge because it's a positive function, right? So you don't really have to worry about that in the variety of cases. But sometimes when you're dealing with, say, sine of x over x, um, and you were to place a parameter somewhere in there and interchange the order of integration, it wouldn't work because if you think about the integral from 0 to infinity of sine of x over x, if you replaced sine of x with absolute value of sine of x, it no longer converges. So that's the idea behind this. So I will not be showing that Fubini's theorem is satisfied in this video, but in most cases it's going to be satisfied, and you can pretty much just look at it and it'll see. But again, if you want a more rigorous approach, then I invite you to use Fubini's theorem. So let's go ahead and jump right into the Laplace transform. So here's the definition of the Laplace transform. It looks a little bit random, right? The Laplace transform of f of t is a function of s, and it's the integral from 0 to infinity of f of t times e to the negative st with respect to t. So again, it looks kind of random if you haven't seen it before, but its design is very, very deliberate. And you can kind of see that it generates, when you have a function of t, it's going to transform this function into a different function of s. And so a way to think about this is you have functions in the t world and the s world, and each function in the t world has one function in the s world that it maps onto, and that function in the s world has that function in the t world. And also, luckily, the Laplace transform is one-to-one, meaning that each function has only one transform, and each transform or function in the s world has only one t world function. The kind of exception to this would be functions, for example, f of t equals like secant of t, where there is no function in the s world because that integral simply doesn't converge for any value of s. The classic use for the Laplace transform is differential equations, but we're going to be using it for integration. So I have here a table of Laplace transforms. All of the Laplace transforms that are right here are pretty easy to calculate, except for maybe these last two over here. So really the important ones are going to be Laplace transform of 1, e to the at, t to the a, sine of at, cosine of at, and ln t. Now I have some other ones in here that might be kind of interesting. Hyperbolic sine of at, hyperbolic cosine of at, the unit step function, which is denoted as h of t minus a. So the unit step function just means if the input of the unit step function is greater than 0, then its value is 1, and if the input is less than 0, then its value is 0. So that's an interesting function. Hyperbolic secant is this combination of digamma functions, and hyperbolic tangent is a different combination of digamma functions. These don't show up too often, but they are handy to know in a pinch. Also, much more importantly, right here are the table of Laplace transform rules, and these are very, very, very useful in a variety of cases. So, we have, if we multiply a function by t to the n, and then we take the Laplace transform, it's the same as taking the Laplace transform of the original function and multiplying by negative 1 to the n, and taking the derivative with respect to s n times. So notice that multiplying by t becomes differentiating with respect to s. Similarly, dividing by t becomes integrating with respect to s. Differentiating with respect to t becomes multiplying by s, and then of course subtracting this f of 0. And then f double prime, you sort of just perform the same operation on f prime that you did on f to get f prime. So you can sort of recursively plug in this formula to get the formula for f double prime, and then you can continue on for f triple prime and so on, but you usually won't have to deal with anything above f double prime. Also, if you stretch or shrink a function, it has this effect on the Laplace transform. It's an opposite stretch or shrink, and also dividing by the stretch factor. Also, if you integrate with respect to t, in this case it's with respect to u, but essentially this is with t, then it's the same as dividing by s. Also, if we multiply a function by the unit step function, then we end up multiplying by e to the negative as right here, which is a little bit interesting. And this may sometimes show up if you want to take the inverse Laplace transform of something raised to a power. And finally, if we multiply by e to the at, this just shifts over the Laplace transform. So all of these rules are really important. Probably the most useful one on a regular basis is this one right here with f of t over t, and this one right here with the Laplace transform of f prime of t, as well as maybe this one right here with the Laplace transform of f of at. And we'll see some cases of that in the future. So first we're going to talk about applying the Laplace transform directly. So many integrals will already be in the form of Laplace transform, so it'll just look like the integral from 0 to infinity of f of t times e to the negative st. And in that case, you're going to want to use those rules of the Laplace transform to go ahead and try and plug in and figure out a situation where you're going to be able to calculate the Laplace transform. Another thing is if we want to integrate, instead of e to the negative st, we have some cosine t or some sine of t, we can use the fact that e to the it equals cosine t plus I sine of t, and then mess around with real and imaginary operators, and we can find that the real part of f of a plus bi, where f is this capital F, the Laplace transform, this is going to be the same thing as the integral from 0 to infinity of f of t times cosine of bt times e to the negative at. And the same thing with the imaginary part, we just have that sign and this negative sign in front right here. So that's also very, very helpful in a variety of situations. If I wanted to integrate some function from 0 to infinity and multiply by sine, then I can just use the Laplace transform, which is nice. And in order to use these real and imaginary operators, f of t does have to be a real function. And another very, very important one, if we just have the integral from 0 to infinity of f of t dt, but let's say f of t doesn't have a nice antiderivative, but it does have a nice Laplace transform, then we can just take the limit as s goes to the 0 plus, or approaches 0 from the right, of f of s, and you can just go ahead and plug in, and you see that this is going to be the integral from 0 to infinity of f of t. So if f of s is easy to calculate in the above situations, the Laplace transform can make seemingly difficult integrals ridiculously easy. So here's a really classic example, the Dirichlet integral, and this just gets absolutely destroyed by the Laplace transform. You can see here, this function sine of x over x, it's very nasty since it doesn't have an elementary antiderivative, but because of the fact that sine of x works so well with the Laplace transform, all we need to do is take the limit as s goes to 0 plus of the Laplace transform of sine of t over t. And notice that the Laplace transform of f of t over t is the integral from s to infinity of f of u du, as we showed in that set of rules. So this makes the Laplace transform of sine of t over t just equal to the integral from s to infinity of 1 over u squared plus 1 du, which is just inverse tangent of 1 over s after some simplification. Then we just take the limit as s goes to 0 plus, and we find that our answer is pi over 2. It's that easy. And if we had, say, like an e to the negative t multiplied by the sine of t, all we would have to do to change this is change this from limit as s goes to 0 plus and just evaluate it at s equals whatever that exponential lines up with, right? Here's another cool example, something from a previous video. If we wanted to calculate the integral from 0 to infinity of natural log of x times cosine of x times e to the x, using our formula from above, we can just say this is going to be the real part of the Laplace transform evaluated at s equals 1 plus I, where we're talking about the Laplace transform of natural log of x. Right? So that's this right here. And the Laplace transform of natural log of x is just negative gamma minus ln s all over s. And so our integral I is just going to be the real part of this right here, which is not too difficult to calculate. It's just some algebraic simplification. Just like that, in 2 lines we have gotten done with all the tough integration, and that's it, right? So that's, I think, 2 very, very important tricks to remember, just because sometimes seeing sine and cosine multiplied on the end, or even e to the negative t, can say, oh, that's just another function that's in my way, right? But often when you see that sine, cosine, or e to the negative t, that's actually something that's going to make it easier for you because you can just invoke the Laplace transform. And again, as I've said, with most simple functions, the Laplace transform is incredibly easy to calculate using those rules that we discussed. So here are some straightforward tricks. If we have some function f of x and we're dividing by 1 minus e to the negative x dx, this is going to end up being the sum from n equals 0 to infinity of the Laplace transform of f of x evaluated at n. And the reason for this is if you expand 1 minus e to the negative x as a power series, you just end up with an infinite series of f of x times e to the negative x times e to the negative 2x times e to the negative 3x. And that's just a really, really simple way to express this integral as an infinite series, as long as this Laplace transform is relatively easy to calculate. Then on the same note, if we have a plus sign here, it's just this, it's just got this alternating series right here. So again, not too difficult to calculate. So let's go ahead and go into some practice problems for those methods right up there. I advise you to go ahead and try these right now. Alright, so hopefully you were able to figure all of those out. I don't think that they were too difficult of a practice problem, but yeah, so hopefully if you have any questions on these practice problems or want any help, feel free to join my Discord, and I'm always happy to answer questions. So let's go ahead and move on to the next problem, or the next topic, I guess. So this is a little bit of a different use of the Laplace transform, and we're going to be using it in a very different way than we did before. So this is where we're going to be introducing a parameter, and this is something that I discussed in my last video about Feynman integration, and this is going to be almost the exact same situation. So I'm going to go ahead and make some comparisons between Feynman integration and the Laplace transform. So with Feynman integration, we start with some integral I, which is the integral from a to b of f of x dx. Then we introduce a parameter v, and so we write this function I of v, which is equal to the integral from a to b of f of x and v. And if we plug in a certain value of v, we're going to get the original f of x from before. So then we differentiate with respect to v, and we end up with the partial derivative with respect to v inside the integral. And this ends up making our integral easier to solve, and so we're able to evaluate it. And then we get our original I of v function back just by integrating I prime of v. Now with the Laplace transform, we have the exact same story. So with the Laplace transform, we introduce a parameter, v, in this case. Then we take the Laplace transform on both sides. So what does that mean? Well, that means we just multiply by e to the negative sv, right? Taking the Laplace transform, and then integrate from 0 to infinity dv. Then, what we actually are able to do is we invoke Fubini's theorem, and we interchange the order of integration. So we bring this a to b integral outside, and on the inside we're going to have the integral of e to the negative sv times f of x and v dv, which is just the Laplace transform of f of x and v. Note that this is the Laplace transform with respect to v, not with respect to x. And so sometimes integrating this Laplace transform is a little bit easier, and then we're able to integrate this, and then once we have the Laplace transform of I of v, we just take the inverse Laplace transform on both sides. So I have this right here. I think it's kind of funny. Why would I want to do this? Because it sounds like taking the Laplace transform and then the inverse Laplace transform just makes everything more complicated, right? But the reason for this is the way that the Laplace transform works is very interesting. It maps functions from the t world to the s world in a very interesting way. So if you have an exponential function or a sinusoidal function in the t world, or in this case we're using v instead of t because t sometimes just looks like a plus sign, which is confusing. So um, if you have a integral exponentials and sinusoidal functions become rational functions in the s world. So if you have, for example, sine of vx in this example, and then I take the Laplace transform, I'm changing v to s. Well, it's actually going to become a rational function because the Laplace transform of sine of vx with respect to v is just x over x squared plus s squared. And this just becomes a rational function, which is super, super easy to integrate. And similarly with exponentials, exponentials just turn into rational functions as well, actually reciprocal functions. And so sometimes these integrals, this is actually the same problem as before, but very often um, it's going to be helpful to actually convert sine of x into a rational function. So I'm going to go over some other examples, hopefully to make this a little bit more clear. Um, but here in this example, we have sine of vx, and then we decide to take the Laplace transform. It becomes a simple arctangent integral, and we get that the Laplace transform is pi over 2s. Taking the inverse Laplace transform, we get that I of v is just equal to pi over 2 for any value of v greater than 0. Very, very important thing to note here is that the Laplace transform will always report a value um, if the Laplace transform converges for any value of s. So one example of this is the Laplace transform of sine of x only converges if s is a positive number. If s is 0 or negative, it's not going to report any number. It's not going to converge, right? However, we can still plug in a value of s and we'll still get a number out. So that's something to make sure to check for. And in this case, for I of v, we have to make sure that if we take the Laplace transform with respect to v, um, the the Laplace transform integral is going to converge regardless of the value of v and the value of s. So that's something always just to check for. Make sure you don't have any functions that behave wildly like secant of x or tangent of x. That's not a good idea for a parameter for your Laplace transform. So something that's a little bit different in this situation is that placing the parameter for the Laplace transform is usually a lot easier than actually choosing the parameter for Feynman integration, because with the Laplace transform, it's almost always going to go inside of a sine function or an exponential function. And the reason for that is essentially, how do I put this? With the Laplace transform, it's just not as useful in as many situations. So whenever you see that sine and something that might look like it might be nice if it were a rational function, I would just try plugging in sine of tx and then taking the Laplace transform just because of how it works. And something else that's very interesting is the inverse Laplace transform can also be represented by an integral. I don't have the definition here because it's a little bit daunting, but we can also interchange the order of integration. So for example, if we instead of defining some function I of v, we just define some function f of s is equal to the integral of f of x and s dx, then we can take the inverse Laplace transform on the inside and on the inside of that integral. It does require Fubini's theorem, but again, just make sure that function is positive or bounded. So here's an example here. It's a little bit convoluted, but we're using the fact that the Laplace transform of sine of t over t is the inverse tangent of 1 over s. And so if we wanted to evaluate this integral here, which looks absolutely nasty, all we have to do is plug in I of s equals inverse tangent of x over s, and then using the rules of the inverse Laplace transform, we find that the inverse Laplace transform of I of s is x sine of tx over cos of x, which also looks daunting, but I can tell you that this first integral right here is completely impossible to solve in its current form. This integral right here, just using a common integral formula and Feynman's technique with differentiating under the integral sign, it's actually not too difficult to calculate. So it's not easy to calculate necessarily, but it's way more possible than this problem right here. And then once we calculate it, all we have to do is take that Laplace transform in the forward direction and go ahead and evaluate our integral. So that's pretty nice. So parametrization and the application of the Laplace transform or inverse Laplace transform is not very common, so it only applies to a few specific cases, which is, again, what makes it so much easier to use because there's so few cases that you actually have to remember. So here we have for the Laplace transform, if you have some function f of x times sine of x, if you write this as a function, I of t is f of x times sine of tx, and then you take the Laplace transform, you're going to end up with f of x times x over x squared plus s squared. So for example, if you had some natural log in your f of x and some, I don't know, some other functions, then natural log does not work very well with sine of x, but it does work pretty well with x over x squared plus s squared, because we can go ahead and apply our generalized formulas for integrals of rational functions, or if f of x is just any rational function in general. And same thing with cosine of x, except we end up with an s outside and no x on the inside. And with the inverse Laplace transform, it's pretty much just going exactly in the opposite direction. So if we have some f of x over x squared plus s squared, we can convert it to f of x times sine of x over x, which is nice if our function of x is something that works well with sine of x. And another one right here, sorry, I kind of screwed up this f of x right here, but you can see in that upper example that we had that inverse tangent of x, which is generally not fun to deal with, but using the Laplace transform, we can turn that inverse tangent into something completely different. So as you can see here, um, integral of f of x inverse tangent of x can be converted into an integral of x times sine x times f of x dx. And finally, we're going to get to our coolest and most powerful trick yet right here, which is called the Mas identity. Now, I want to go ahead and give a shout out to Mathematics My, one of my absolute favorite integration channels with the best problems out there. In my opinion, hasn't been active for a while, but absolutely some awesome content, and he gave me this is actually the first place that I ever saw this identity. So this is arguably the most powerful tool relating to the Laplace transform when it comes to solving integrals. It does rely on Fubini's theorem, which means that it's not going to work in all cases. For example, if g of x and f of x don't work very nicely or are sort of erratically behaving functions. But this is an absolute destroyer of Dirichlet and Borwein integrals, which I'll discuss in a moment. So this states that the integral from 0 to infinity of f of x times g of x dx is the same as the integral from 0 to infinity of the Laplace transform of f of x times the inverse Laplace transform of g of x. It doesn't matter the order of the functions here. I said it backwards. But it doesn't matter which one is Laplace and inverse because it's symmetric with respect to f and g. And this is most useful when we have an integral from 0 to infinity of some trig function over x to the p, or some trig and exponential functions over x to the p as well. And as for proof of this, I'm not going to supply one. You can find a proof of it on one of my previous videos on the Borwein integrals or on Mathematics My, but overall it's not too difficult to prove and it's pretty straightforward. So I think you guys can also probably prove it yourselves if you wanted. So I have an example right here with some trig. So usually to solve this, we would use Feynman's trick and combine it with some trig identities. But in this case, we're going to say our f of x is 1 minus cosine of x, and our g of x is 1 over x squared. Now, when we take the Laplace transform, usually we change the variable name as well. In this case, we're just going to keep the variable name as x through. So the inverse Laplace transform, in this case, of 1 over x squared is just going to be x. And the Laplace transform of 1 minus cosine of x is going to be 1 over x minus x over x squared plus 1. So applying this just becomes a simple rational integral, and when you simplify, it just becomes the integral from 0 to infinity of 1 over x squared plus 1, which is pi over 2. So if you want, you can go ahead and try this. This is the second Borwein integral right here, which I would definitely suggest you give a try, since it's best accomplished using this method. Alright, now I have some practice problems on the last few things we discussed. I absolutely would suggest you go ahead and give these a shot, especially because this is the end of the video, and hopefully you have learned how to do all these problems. So yeah, go ahead and give all of these a try. Note that this is an especially hard problem, so please attempt this last and only if you are really, really determined. Alright, so hopefully you were able to solve all of the problems shown up here. If not, you can always ask for me for help in the Discord, and I can go ahead and try and walk you through. Thank you guys so much for watching this video. I hope you enjoyed everything and everything was to your liking. You know what I just realized? This problem right here, where did I get it from? Because this integral doesn't converge. Okay. Don't try this problem. Yeah, don't try that one. Sorry about that. Anyway, I hope you guys enjoyed the video and you learned a lot. Go ahead and leave any suggestions you have for future videos down in the comments, and I'll try to get to all of them. And yeah, I hope you guys enjoyed the video. I hope you learned something, and I will see you next time. Thanks. Bye.